Welcome to the Twin Labs podcast, where we help you make better decisions using AI and digital twins. Right now, on corporate servers all across the world, there are just, well, billions of dollars of absolute engineering brilliance sitting locked in digital folders, completely useless.
Oh, absolutely. Literally just gathering digital dust.
Exactly. I mean, if you are a decision maker tuning in today and you've signed off on a massive simulation project recently, there is a very good chance your company owns one of these incredibly expensive, incredibly dormant digital paperweights.
Yeah, and it's really the ultimate paradox of enterprise technology right now. We have spent half a decade building these digital systems that understand the physical world better than we do, and yet the people who actually run the physical world on a daily basis have zero access to them.
And that is exactly the problem we are tearing apart today. Today is March 28, 2026, and we're doing a deep dive into a highly influential, newly released briefing from Twin Labs.
Right, the one titled Transforming Business with Executable Digital Twins in 2026.
That's the one. And our mission here is to deconstruct this massive paradigm shift that's happening right under our noses. We are moving away from those complex, highly technical digital twins that just sit there doing nothing, and we're moving towards something called executable digital twins, or xDTs.
Which is such a crucial shift because these xDTs are tools built not for the data scientists sitting in a laboratory, but for the everyday operations teams out on the floor.
Right, the people actually doing the work. Which means this conversation is built specifically for you, the listener. Because, I mean, if you are leading teams, allocating budgets, or just staring at a spreadsheet trying to figure out how to squeeze actual value out of your AI investments, you need the operational reality, not just the academic theory.
Exactly. We're going to extract the core lessons from this briefing on how you deploy intelligent simulation-grade systems that create true ROI, build trust, and, establish unshakable authority in your daily business operations.
So let's start with the central contradiction, the briefing highlights right out of the gate. Think back to the era, roughly between 2019 and 2022. Every major company was obsessed with building these incredibly accurate physics-based digital twins.
Oh, yeah, they were engineering marvels.
Yeah.
I mean, they mapped every bolt, every thermal dynamic, every fluid flow of a factory or a product.
But, and here's the kicker, if you walk into a boardroom today and ask the executive team, hey, who used that multi-million-dollar model last Tuesday to make a decision? The room just goes completely silent.
Yeah, it's the sound of people suddenly finding the grain of the conference table incredibly interesting.
Right, everyone just looking down.
And we really have to start by establishing this core problem, what the briefing calls the ROI reckoning. Because we can't really talk about the solution, the executable digital twin, without first understanding the massive financial and operational pressure of this pre-2026 status quo.
Which was all about prestige, right?
Exactly. Historically, these massive digital twins were treated as prestige assets.
Prestige assets, like buying a corporate art collection to hang in the lobby. It shows everyone you have money and taste, but it doesn't actually manufacture anything.
In many ways, they were treated exactly like corporate art. I mean, they lived in academic research papers, or they sat on a dedicated, wildly expensive specialist workstation in the corner of a thermodynamics lab somewhere.
Just sitting there looking smart.
Right. They were funded almost entirely as innovation initiatives. During that tech boom, the whole point was just proving to the market or to the board of directors that a company took intelligent systems and digital transformation seriously.
So they were basically a signaling mechanism.
100%.
Yeah.
But they were rarely, if ever, actually touched by the operational staff who run the business day to day.
It was an exercise in corporate PR. Like, look at us. We are a digital-first enterprise. We have a digital twin of our entire supply chain. But now, 5 years later, the economic reality has really set in. The honeymoon phase is definitively over.
Oh, completely over. The finance teams are looking at the ledgers, and they are demanding ROI. The core question has fundamentally shifted from, can our engineers build one of these mathematically perfect things, to what has this thing actually changed about how we do business on a Tuesday morning?
Which is a very harsh question to answer for a lot of teams.
It is. And from a psychological and business perspective, this shift in expectations is massive. Think about it from the perspective of a plant manager, right? You can have a highly accurate, flawlessly coded simulation of a manufacturing cell. It calculates thermal expansion to the micrometer.
Sounds great on paper.
Sure, but that model is practically useless unless it is demonstrably reducing unplanned downtime or improving your daily output efficiency or, cutting your energy bill. The defining challenge of 2026 is bridging the gap between a twin that simply exists and a twin that actually works.
Right, because a model sitting in a data scientist's locked folder is not an operational asset. It's an incredibly expensive theoretical document. I have to challenge this premise just a bit, though. I mean, for my entire career, the gospel of data science and simulation has been that the closer your digital model mimics physical reality, the better.
That's definitely the traditional mindset, yeah.
Right. So when you say accuracy isn't enough, it feels counterintuitive. If I have a perfect model, shouldn't that be the ultimate tool?
Well, it is the ultimate tool, but only for the person who knows how to hold it. And that is the fatal flaw of the prestige asset era. The tool is so complex that it essentially has no handle.
Okay. Reading through the Twin Labs briefing, an analogy kept coming to mind. It's like, say a logistics company decides they need to be faster, so they go out and buy a multi-million-dollar Formula One race car.
Okay, I like where this is going.
They park it in the company garage. They have the shiny paint job, the prestige of telling everyone they own an F1 car. But there is literally only one engineer on their payroll who knows the complex 30-step startup sequence to even turn the engine over.
That is a phenomenal way to look at it.
So, on race day, which in this context is the daily operational grind of your business, moving freight, fixing machines, the car is just a museum piece.
Right.
The CFO is standing in the garage asking, "We paid for a race car, where are the delivery results?" And the engineering team's answer is, "Well, the car is theoretically capable of going 200 miles an hour, but our truck drivers don't know how to use the steering wheel."
What good is the theoretical top speed if the car never touches the actual track?
Exactly. You can't just mandate that your truck drivers learn to drive an F1 car. I mean, they have actual freight to move. They don't have time to get a PhD in aerodynamics.
Right, they have a day job.
Because the old prestige models are completely failing this ROI test, the underlying architecture fundamentally had to change. You can't just train the driver to use a worse steering wheel. You have to redesign the engine so it fits inside a delivery truck.
Which leads us directly into the technical evolution we are seeing this year, the Executable Digital Twin, or xDT.
Yes, exactly. So if the Prestige Twin is the F1 car locked in the garage, what exactly makes this new breed of digital twin executable? Like, how is the architecture actually different?
Well, if we break it down to its core components, an xDT is a lightweight, portable, ready-to-run version of a digital twin that is specifically designed for everyday operational use.
Okay.
It takes all that essential intelligence from the heavy physics-based model and packages it into a self-contained API-driven unit. If you are familiar with modern software development, it's very much like a containerized microservice.
Okay, I want to stop you right there because I am putting myself in the shoes of a VP of operations listening to this who hasn't written a line of code in 20 years. You just used terms like API-driven unit and containerized microservice?
Right, fair point.
What does that actually mean for my IT infrastructure? Why does that matter to my daily operations?
That is a very fair call-out. Let's strip away the software jargon. Think of a traditional digital twin like a massive custom-built factory machine that has to be bolted to the floor in a specific room.
Okay, a big, heavy machine.
Right. It needs special power outlets, special climate control, and a dedicated team just to turn it on. In software terms, traditional models were incredibly brittle. They were tightly coupled to specific installations, requiring massive geometry files, material libraries, and, specific solver licenses that only ran on a massive server.
So it was heavy and entirely immovable.
Exactly. Running them required deep expertise just to format the raw data into something the software could understand, and then even more expertise to interpret the output.
So it was a bottleneck.
A huge bottleneck. Now imagine taking the intelligence of that massive machine and putting it inside a standard shipping container. That shipping container has universal plugs on the outside.
Oh, I see.
You can drop that container anywhere in the world, plug it into any standard power grid, and it does its job perfectly without you needing to look inside the box. That is what a containerized microservice with an API is. The xDT breaks the coupling to the heavy software.
That makes a lot of sense. The Twin Labs briefing actually outlines 3 defining characteristics of an xDT to make this possible. First, it is portable, meaning I could run it in an AWS cloud instance in Seattle, or I could run it on a ruggedized server sitting next to an oil rig in the middle of the North Sea, and it behaves exactly the same way.
Spot on. Because it's in that universal shipping container, the environment doesn't matter. Second, it is configurable. Non-experts can adjust the parameters without needing to understand the complex math happening underneath.
Right.
The API, which is that universal plug on the outside of the box we talked about, only exposes the dials that actually matter for a decision.
But the third characteristic is where we really need to dig in, because this is the controversial part. To make it executable, to make it run on an oil rig or an iPad, it has to be lightweight. The briefing notes that instead of taking hours to run a full finite element simulation, it uses something called surrogate modeling to deliver results in milliseconds.
Yes, and this is the true breakthrough of 2026.
But here is where I have a massive problem. To get that millisecond speed, there is a fundamental trade-off. You are trading ultimate mathematical fidelity for speed.
Yes, you are.
The briefing explicitly states that an xDT captures about 80 to 95% of the behavior of the full physics model. Now, I have to challenge you on this 85% accuracy trade-off.
Bring it on.
If I am the leader of a company and I'm paying millions for AI and simulation, why am I suddenly supposed to accept a B- grade on the physics? I mean, in industries like nuclear power, aviation, or chemical refining, missing 15% of the physics behavior means things explode and people die. You can't just surrogate away safety. How is this not incredibly reckless?
I am really glad you pushed back on that, because it is the exact reflex every senior engineer has when they first encounter surrogate modeling. It feels like you are compromising your integrity, but you have to separate safety-critical boundary testing from daily operational optimization.
Explain that difference.
Okay, if you were designing the containment vessel for a new nuclear reactor, and you need to know exactly how the metal will deform under a 1 in a million pressure spike, you do not use an xDT.
Obvious.
You use the massive, heavy, 99.9% accurate, full physics model, and you let a supercomputer chew on it for a week. That is safety-critical edge case testing.
Right.
But if you are the shift operator of that same plant, and you just need to know the optimal flow rate for the secondary cooling loop based on today's ambient weather to save 3% on energy costs without tripping an alarm.
You don't need the supercomputer.
Exactly. You don't need to simulate the atomic deformation of the metal. You just need to know the thermal flow within a very specific, perfectly safe operational band.
So it's really about the context of the question being asked.
Exactly. Let's use a mechanism-based metaphor to explain how this surrogate modeling actually works, because it helps clarify why it's safe.
Let's hear it.
Think about compressing a massive, high-resolution raw photograph from a professional camera. The raw file is, say, 500 megabytes.
Yeah.
It contains data on every single photon that hit the sensor. It takes your computer a few seconds just to open it.
Right. It's incredibly heavy.
Now, you compress that raw file into a 2 megabyte JPEG image. Technically, mathematically, you have permanently lost microscopic pixel data. You traded fidelity for file size.
Right.
But when you look at that JPEG on your phone, to the human eye, it is the exact same picture. It captures 95% of the visual information, and crucially, it loads in a millisecond. If your goal is to quickly show someone a picture of a bridge, the JPEG is infinitely more useful than the raw file.
Okay, that makes a lot of sense. But how does the AI actually create the JPEG of a physics model? The briefing mentions physics-informed neural networks, or PNs, and Gaussian process surrogates.
Right, those are the engines.
Again, pretend I am a business leader who only knows AI from playing around with chatbots online. Is this surrogate model just blindly guessing based on patterns, like a chatbot predicting the next word in a sentence? Because if it's just guessing, I still don't trust it.
That is the brilliance of these specific techniques. Let's take the physics-informed neural network, the PIN. Traditional machine learning, like the AI that writes your emails, is a black box.
Yeah.
It looks at millions of examples and guesses the most likely pattern. If you feed it bad data, it guesses wildly wrong things. It has no underlying concept of reality.
It doesn't actually know what gravity is, right? It just knows the word gravity often appears next to the word falling.
Exactly. But a physics-informed neural network is completely different. The engineers literally hard-code the fundamental equations of physics, like the Navier-Stokes equations for fluid dynamics or the laws of thermodynamics, directly into the AI's learning process.
Wait,
Yes. The AI is penalized during its training if it ever tries to guess a result that violates the conservation of mass or energy. So it literally cannot hallucinate that water flows uphill. It is mathematically constrained by reality.
wow. So it has guardrails built into its very architecture.
It does. It learns the relationship between the inputs and outputs of a heavy, slow model, but it finds mathematical shortcuts to get to the answer in milliseconds without ever violating the laws of physics.
That's incredible.
And Gaussian process surrogates do something similar with advanced statistics. Instead of measuring every single millimeter of a landscape with a tape measure, which takes years, it takes 50 highly accurate measurements and uses probability to draw a flawless curve between them.
So back to the 85% accuracy concern. You are saying that an 85% accurate surrogate model that your shift supervisor actually holds in their hand and uses every single morning vastly, overwhelmingly outperforms a 99% accurate model that sits completely inert on a server.
Unquestionably. It is the difference between having a theoretically perfect atomic-level compass locked inside a titanium safe versus having a slightly less precise standard magnetic compass that you are actually holding in your hand while you are lost in the woods.
The perfect compass is useless to the person freezing in the forest.
Exactly.
Yeah.
If you need to make a decision right now on a factory floor, an answer that takes 5 hours to compute is indistinguishable from having no answer at all.
And this isn't just a theoretical debate about physics, by the way. This exact principle, that an accessible and embedded system fundamentally beats a perfect but inert one, is the core philosophy driving Twin Labs' entire approach to AI-powered learning and intelligence systems.
Yes, it is.
They've built their whole framework around the idea that the user's ability to engage with the tool is just as important, if not more important, than the raw math inside the tool.
It is a profound shift in organizational mindset. You are moving away from optimizing for mathematical perfection, and you are shifting entirely to optimizing for human utilization.
Which brings us to a massive practical hurdle. We have this fast, portable API, the xDT. It's lightweight, it's containerized, it's physics-informed. But let's be completely real here.
Let's do it.
A shift supervisor, a maintenance worker, or a sustainability manager is not going to open up a command line interface on their laptop and start pinging a server with raw JSON code. How does a non-technical worker actually interact with this intelligence?
I don't want to see code, that's for sure.
Right. This brings us to Section 3 of the briefing, the missing link of low-code platforms and the concept of the Twin app.
This is where the rubber finally meets the road and where the ROI is actually generated. The xDT itself, as brilliant as it is just a back-end building block. It's the engine block of the car sitting on a pallet. The Twin app engine, which relies on modern low-code development platforms, is what actually converts that raw mathematical engine into a usable, everyday vehicle. Yeah. It abstracts all of that model complexity behind a purpose-built, highly visual interface that runs securely in a web browser or on a standard mobile device, and it connects directly to live data sources.
So if the xDT is the engine, the low-code app is the dashboard, the steering wheel, and the pedals.
Exactly.
You don't need to understand how the electronic fuel injection mathematically calculates the air-fuel mixture to drive to the grocery store. You just press the gas pedal, and the car abstracts the complexity away from you.
That's a perfect visualization. To make this concrete, let's really dive deep into the water utility example from the briefing, because it perfectly illustrates the before and after states of this technology.
Let's do it. Paint the picture for us.
Imagine a maintenance engineer at a large municipal water treatment facility. Say 6:00 a.m., she's starting her morning shift. There's a massive heat wave rolling in, and she knows that sudden temperature spikes cause ground shifts, which put immense stress on an aging underground pipeline network.
High stakes, real-world physical constraints.
Exactly. Now, 5 years ago, in the prestige asset era, how would she figure out which pipes were at risk of bursting today? She would have to go back to her desk, write an email to the centralized data science team requesting a simulation run.
Ugh.
The data science team would have to manually pull the weather forecast, manually pull the current flow weights from the sensors, format all that data, and feed it into their heavy finite element model.
Which takes hours to run.
Hours, if not days.
Yes.
3 days later, the engineer would receive a beautifully formatted 40-page PDF report detailing the stress fractures on the pipe network.
But by then, the heat wave is over, and the pipe either survived or it already burst and flooded a neighborhood.
Right.
The report is highly accurate, but operationally completely useless. It's an autopsy, not a prediction.
Exactly. It's an autopsy. Now, fast forward to today, 2026, using an executable digital twin and a twin app. Same engineer, same heat wave at 6:40 a.m. She doesn't email anyone.
Oh, nice.
She pulls an iPad out of her truck and opens a secure, low-code application. The app is already pulling in live, real-time incoming flow rates from the facility's IoT sensors. The user interface doesn't show her complex fluid dynamic equations, it just has a few simple sliders. She manually adjusts the slider for the ambient temperature parameter to match the forecasted heat wave.
So she's interacting with the physical variables, not the mathematical variables.
Right. She taps a button on the screen that says, run 24-hour predictive scenario. The app sends those simple parameters through the API to the xDT sitting in the background. The surrogate model runs the complex physics math in milliseconds. Milliseconds. The app receives the answer and instantly displays a simple visual curve showing failure probabilities across the network. It flashes red over 2 specific pipeline junctions and recommends scheduling 2 physical inspections for the afternoon when the heat peaks. She taps schedule right there in the app, and the work orders are dispatched.
The entire process takes 4 minutes. 4 minutes.
Yeah.
0 emails to the data science team. 0 waiting for compute time. She had the power of a supercomputer, but the user experience of checking the weather on her phone. That is the holy grail of operational efficiency.
And what makes this possible from an IT perspective is the underlying input-output contract. The low-code platform itself doesn't do any of the heavy math. It just handles the data ingestion from the sensors and draws the buttons on the screen. The xDT sits completely segregated securely behind a REST or GraphQL API, handling all the physics calculations.
Okay, you lost me again at GraphQL API. If I'm paying the IT budget, why do I care how the app talks to the math?
You care deeply because it prevents chaos. In the old days, if 5 different teams needed to use a model, the engineers would literally make 5 copies of the software file.
Oh man, I know that pain. You end up with files named like model final 3 use thesis and Steve edit.xcells. And nobody knows which one is actually correct anymore.
Exactly. It creates a governance nightmare.
Yeah.
By using a stripped API, which is essentially a secure doorway where the app passes a question through the door and the xDT passes the answer back out, you establish a shared service architecture. You only have one single, highly validated model locked in the server.
Right.
But 50 different apps can pass questions through the door. The maintenance team has an app looking at pipe failure. The energy management team has a completely different app looking at power consumption. The finance team has an app looking at raw material costs. But they are all pinging the exact same single source of mathematical truth.
And as the briefing points out, Twin Labs has proven this extensively in other domains as well.
Yeah, they have.
For example, when large enterprises try to scale AI-powered learning environments, they require this exact same shared service architecture. You can use it to personalize training content, analyze skill gaps, and monitor learner progress for thousands of individual employees, all without having to build a bespoke, standalone AI model for every single user.
Right, which would be impossible.
Exactly. You just have one central intelligence engine and multiple personalized interfaces interacting with it.
It is genuinely the only way to scale intelligence across a massive enterprise. If you build a bespoke model for every problem, your IT infrastructure just collapses under its own weight and maintenance costs.
Well, if the low-code platforms and the APIs are doing all this heavy lifting, it makes me wonder why we didn't just build this exact architecture back in 2021. This brings us to Section 4, the 2026 inflection point. What changed in the background to make this suddenly viable today? Because technologies don't just break through in a vacuum.
No, they definitely don't. They break through when economic pressure and technical capability violently intersect. The Twin Labs briefing identifies 4 massive external pressures that have converged specifically this year to create this inflection point.
Let's go through them.
First, and perhaps most importantly, is the ROI imperative we talked about earlier. Those massive pilot programs from 2019, 2022, they have matured. The grace period for innovation is over. Finance leaders are demanding concrete, quarterly outcomes, and xDTs are the only proven way to translate deep simulation into operational value at scale.
Right, the CFO is no longer impressed by the 3D VR rendering of the factory floor. They want to know how many dollars it saved yesterday.
Exactly.
What's the second pressure?
The second is edge computing demand. Over the last 5 years, industrial IoT has absolutely exploded. You now have thousands of sensors on factory floors, inside oil rigs, and spanning power grids. You are generating terabytes of data every minute. You literally cannot send all that data back to a centralized cloud server.
Wait, why not? The cloud is supposed to have infinite capacity.
Because of the speed of light and network latency?
Oh, right.
If you have a critical high-pressure pump that starts vibrating erratically, sending that vibration data all the way to a cloud server in Virginia, running a heavy simulation, and waiting for the answer to travel back might take 3 or 4 seconds. In a highly volatile industrial setting, 3 seconds is the difference between an automated controlled shutdown and a catastrophic explosion.
That's terrifying.
Yeah. You need the intelligence to live locally, right next to the machine. An edge-deployed xDT sitting on a local server the size of a shoebox can process that data and trigger the shutdown in less than a millisecond.
Wow. Milliseconds literally save millions of dollars and potentially lives.
So we have the economic push for ROI and the hardware push at the edge. What is the third factor?
The third pressure is surrogate model maturity. The math has finally caught up to the ambition. Those techniques we discussed, the physics-informed neural networks and Gaussian processes, have advanced incredibly fast over the last 36 months.
So they're reliable now. Extremely. The gap between a full-order mathematical model and these lightning-fast machine learning surrogates has essentially closed for operational purposes. The deep engineering confidence is finally there. 3 years ago, relying on a surrogate model to dictate a chemical mixing process might have felt like a massive gamble to a plant manager. Today, it is genuinely, provably fit for operational purpose.
Let me play devil's advocate for a second.
Go for it.
Let's say I'm listening to this and I run a mid-sized manufacturing firm. This all sounds great, but it also sounds like the bleeding edge of enterprise tech. If I sit back and wait until 2028 to adopt this, let the massive Fortune 100 players work out all the bugs and suffer the early failures, why aren't I just being smartly cautious? Why jump in now and risk the capital?
That brings us exactly to the fourth and final pressure, standardization. 3 years ago, your caution would have been completely justified. It was the Wild West. Everyone was building proprietary models that couldn't talk to each other. But industry bodies have spent the last few years aggressively converging on API-first, format-agnostic interoperability standards. The fundamental rules of the road are now written and agreed upon.
So the foundation is poured.
Exactly. If you wait until 2028, you aren't avoiding bugs. You are just bleeding ROI to your competitors who are already optimizing their daily operations with standardized tools. Building your architecture to align with these standards today means you won't be rebuilding from scratch later. Waiting just means you are intentionally leaving money on the table while your competitors' shift managers are making optimized decisions in 4 minutes.
Okay, the tech is ready, the standards are set, and the finance team is breathing down your neck. The listener understands the landscape. Now, let's get incredibly practical.
Let's do it.
Section 5 of the briefing provides an exact 4-step playbook for decision makers. This is the blueprint for execution to build authority and trust in an organization. Step 1. Identify a high-pain, model-ready process. Let's really unpack this, because what does model-ready actually mean?
This is where most digital transformation projects die before they even begin. The biggest, most fatal mistake a leadership team can make is trying to build a brand new digital twin from scratch for their most chaotic, undocumented, historically messy process.
But it's so tempting, isn't it? As a VP or a director, you want to take your newest, shiniest AI tool and point it directly at the most broken, chaotic process in the company to prove its ultimate value. You want to slay the biggest dragon. You want the hero story for your quarterly review.
It is intoxicating, yeah, but it is a recipe for a multi-million-dollar failure. If a process is chaotic and poorly understood by your human experts, an AI is not going to magically organize it. Step 1 is about finding an existing, validated model that is currently gated by experts. You are looking for a process where some form of predictive logic or formal math already exists in your company, but the bottleneck is accessibility.
Give me a concrete contrast. What is a terrible process to start with versus a perfect one?
A terrible process to start with would be your entire global end-to-end supply chain logistics. It involves hundreds of external vendors, unpredictable weather, human geopolitical factors, and messy data formats. Trying to build an xDT of that as your first project will take 5 years and fail.
And a perfect process.
A perfect process would be a single massive chemical mixing tank in one of your facilities. The physics of how those chemicals mix under heat and pressure are perfectly understood. In fact, your lead chemical engineer probably built a highly accurate simulation of it 3 years ago. The math works. But right now, the shift workers on the floor don't have access to that simulation. They adjust the tank's temperature based on a sticky note left by the previous shift, or their own informal gut feeling of how the tank sounds.
So you find a smart model that is currently locked in a dumb analog workflow.
Precisely. The xDT's job in step 1 is just to bridge the gap between what the expert already mathematically knows and what the shift worker can instantly access.
That makes perfect sense. So you've identified the chemical mixing tank. What is step 2?
Step 2. Package the model as an xDT. This is the heavy technical lifting performed by your data engineering team. They take that existing high-fidelity model from the chemical engineer and apply the model reduction techniques we discussed, the surrogates. They wrap it in that containerized service. They document the strict API contract.
The API contract meaning here is exactly the data you are allowed to send the model, and here's exactly the format the answer will come back in.
Right. And most importantly, they establish the mathematical boundaries. They define the absolute minimum and maximum temperatures the surrogate is validated for. Then they store this packaged unit in a secure central internal registry.
The briefing mentions that practical implementation guides, like the 1-hour guide, are specifically designed to help teams through this step. They help organizations structure this technical documentation in a way that non-specialists can actually understand, audit, and approve. Because if you mess up the packaging in the API contract here, everything downstream breaks.
Exactly. You need structured technical documentation, which leads us to step 3, which is often the make-or-break moment for adoption. Connect to live data and build the Twin app. You use your low-code platform to connect to live operational data, like your IoT sensors on the mixing tank. But the crucial discipline here is designing the app interface around the decision, not around the model.
Explain that distinction, because that feels like a massive psychological trap a lot of brilliant software engineers fall into.
It is the most common trap in the industry. When an engineering team builds an app to interface with a model they spent months perfecting, they are intensely proud of it. They want to expose every single dial, slider, physics variable, and 3D graph the model can handle. They want to show off its absolute power.
Sure, they want to show their work.
But if you give a shift supervisor on a factory floor a dashboard with 40 sliders, 12 chaotic graphs, and a constantly spinning 3D rendering of a tank, you alienate them immediately. They're trying to do a job, not fly a spaceship. They will close the app and go back to using their sticky notes.
It's the difference between the cockpit of a commercial airliner and an ATM. One requires months of dedicated training just to understand what the dials mean. The other is designed so intuitively that you can use it while holding a cup of coffee and talking on the phone.
Beautiful analogy. You have to design around the specific decision the user is trying to make. If the decision for the shift worker is simply, do I increase the pressure by 5 psi or 10 psi to maintain the chemical yield, the app should only ask for the specific inputs relevant to that choice, and it should only display the exact answer to that question. Nothing else. Exposing everything the model can do is a fundamental failure of user-centered design.
And the text notes that advisory support from programs like AI Coach is incredibly valuable here, specifically for helping organizations navigate this psychological hurdle. They help leaders integrate AI into these daily workflows seamlessly, ensuring the technology serves the human operator rather than overwhelming them.
Precisely. You have to treat the human user as the most important component of the system. And that brings us to the final step in the playbook. Step 4. Run a focused pilot and iterate. And the timeline the briefing insists on here is critical 90 days.
Just 90 days.
Yes. You do not do a massive global multi-factory rollout. You deploy it with just one single operations team on one shift. And you measure 3 specific things: accuracy, adoption, and impact.
So, accuracy. Does the surrogate model actually match the physical reality of the mixing tank? Adoption. Do the shift workers actually open the iPad and press the button? An impact. Does the business actually see a higher chemical yield or save time?
Exactly. And you have to expect and actually encourage the need to iterate heavily on the user interface in those first 3 months. Operational users, the people standing on the concrete floor, are ruthless, expert critics of tools that slow them down.
Oh, they absolutely are.
If a button is in the wrong place, or if the app takes 4 seconds to load instead of 1, they will tell you. Their feedback is pure gold. A 90-day pilot with rich, abrasive, honest user feedback is infinitely more valuable than a 6-month pilot that delivers a beautifully polished dashboard that no one ever clicks on.
I want to highlight something really important from the briefing here. I want to remind the listener that utilizing these exact 4 steps is how Twin Labs guides its enterprise partners to turn expensive R&D experiments into daily, profit-driving operational tools. It's not just a theoretical framework, it is a battle-tested operational playbook.
And it requires extreme discipline, doing a pre-deployment readiness assessment, rigorously checking if the model is truly mathematically stable, and if the live data feeds from the sensors are actually reliable, saves massive amounts of expensive rework later.
All right, we've deeply covered the tech, the timing, and the exact deployment playbook. Let's move into section 6, which deals with the profound human element of all this. The text talks extensively about democratization, the true meaning of democratization and the new role of the technical expert. Because when you implement this kind of transformative technology, it fundamentally changes your human workforce. We're no longer just talking about software implementation, we are talking about human capital management and organizational psychology.
This is where a massive amount of internal anxiety sits within organizations. Because when leadership teams start talking about democratizing digital twins or AI-driven automation, the immediate cynical assumption from the technical staff is that the company is going to fire all the expensive simulation experts and let a surrogate algorithm do their jobs.
Right. It's the classic fear, like, the AI is coming for the PhDs. I spent 10 years learning fluid dynamics, and now an iPad app is doing my job.
Exactly. But the reality of this specific shift is the exact opposite. Democratizing digital twins doesn't mean firing your experts. It means taking the incredible predictive power of physics that those experts built and putting it into the hands of plant managers and sustainability leads. It empowers the front line to test interventions safely before committing millions of dollars in physical resources.
Wait, let me push back on this. If the plant manager doesn't need to come to the data scientist and beg for a simulation run anymore, doesn't the expert fundamentally lose their power in the organization? Doesn't the PhD essentially become irrelevant to the daily operation?
It's a very common fear. But what actually happens in practice is a massive strategic upgrade for the expert. Think about it logically. Do you really want your most brilliant, highly paid data scientists spending their days running routine, mundane variations of the exact same thermal model just because a shift worker asked them to? No, that is a waste of their talent.
That's a really good point.
With xDTs and low-code apps handling the routine queries, the expert's role fundamentally shifts. They move from saying, I manually run simulations for people who ask me, to I build, govern, and validate the overall intelligence infrastructure for the entire global organization.
I see. They move from being a short-order cook flipping burgers on demand to being the executive architect designing the menu and the supply chain for the entire restaurant empire.
Beautifully put. And the internal economics of this shift are staggering. In the old model, you had bespoke, per-department engagements. Every single business unit had to hire their own redundant data scientist to build models for their specific problems. It was wildly inefficient. Now, you move to a shared services model. One central elite team of high-level experts maintains a governed portfolio of validated xDTs. The business units simply consume those models through their custom low-code apps.
And there's a hidden benefit here, too. Because these tools are now being used every single day, multiple times a day, by operators on the ground, you get this massive, continuous validation feedback loop. A model that is being pinged 50 times a day in the messy, real world gets stress-tested in a way that a model reviewed once a quarter by an isolated expert committee never will.
Yes, the experts actually get better data on how their models perform. And frankly, this solves the massive talent bottleneck in the industry. You simply cannot hire enough simulation experts to put one in every single factory. There aren't enough of them in the world.
No, absolutely not.
This architecture is the only way to scale intelligence. And as the briefing notes, this perfectly parallels AI-assisted learning contexts. In education and corporate training, a learning designer transitions from manually creating individual pieces of content to designing learning intelligence architecture, a shift that is deeply supported by advisory programs like AI Coach. The human expert absolutely does not disappear. Their leverage just multiplies 1,000-fold.
Okay, we've spent a lot of time talking about the incredible upside, the efficiency, the ROI. But to maintain ultimate credibility with the decision makers listening right now, we have to talk about the dark side. Section 7 of the briefing covers governance, risks, and the terrifying concept of confident wrong answers. If you are a leader signing off on this technology, this is the section that should keep you up at night, because executing this poorly has severe, potentially catastrophic consequences.
It absolutely does. Unbridled enthusiasm for the speed of the technology cannot obscure the very real physical and financial risks. The briefing outlines 3 massive governance failures that inevitably lead to xDT deployments producing confident, highly authoritative wrong answers. The first is ignoring fidelity boundaries.
Meaning the organization forgets that the xDT is an 85% accurate surrogate and starts treating it like the 99% accurate full physics model.
Exactly. Surrogates are explicitly built for operational prediction within perfectly known bounds. They are mathematically interpolating between known data points. They're not for ultra-high fidelity R&D, and they are absolutely unequivocally not for novel failure mode analysis.
Right.
If a massive turbine breaks in a bizarre way it has never broken before, applying a surrogate model to analyze the failure will yield a result that looks totally mathematically plausible, but is practically completely incorrect.
Because the AI is essentially pattern matching within a constrained box. If you show it a pattern it has never seen before, it doesn't know how to say, I don't know. It just hallucinates a plausible-looking guess based on what it does know.
Precisely. It forces the model to extrapolate into the unknown, which breaks the math. The second massive governance failure is a lack of validation documentation. Every single xDT in that shared registry must be meticulously documented with the specific environmental conditions under which it was tested, its precise accuracy metrics, and its explicit operational bounds.
Right, because without this transparency, the downstream user building the app has no way to calibrate their trust in the system.
They might assume a model validated for a factory in freezing Alaska works perfectly for a factory in humid Brazil. And the third failure, input guardrails. This is the most crucial software mechanism. When you give non-experts access to a physics model, you must write software that actively prevents them from entering physically implausible configurations.
Give me an example.
If an operator is using the app and accidentally packs an extra zero into a pressure parameter, let's say they meant to type 100 psi but type 1000 psi.
A simple typo.
Right. The model shouldn't just blindly run the math and spit out a chaotic extrapolated answer. The app interface itself should flag it instantly and say, error. This input exceeds validated physical reality for this equipment. Without those hard-coded guardrails, a simple typo forces the model beyond its validated range, and the user might make a disastrous physical decision based on the output.
And this leads to what I think is the most fascinating and frankly terrifying point in the entire briefing, the cultural risk. A beautifully polished, highly responsive mobile user interface can inspire completely unwarranted confidence in a deeply flawed underlying model. As humans, we assume that visual quality is a proxy for analytical rigor.
I will gladly serve as the harsh voice of caution here. A well-designed, beautiful dashboard that presents unreliable, hallucinated predictions is actually vastly more dangerous to your business than a poorly designed, clunky dashboard. Human psychology naturally trusts things that look authoritative and expensive. If the typography is clean, the latency is zero, and the graphs are crisp, our brains automatically assume the math underneath is flawless.
It's exactly like following a beautifully designed GPS interface on your phone. It has a slick dark mode, a very soothing voice, and it calmly directs you to drive your car straight off a concrete pier into a lake. The software interface is flawless, the cloud latency is great, the data underneath is deadly.
And we've all read the news stories. People will drive right into the lake because the screen looked official and authoritative. Establishing rigid governance frameworks and input guardrails before rolling out xDTs at scale is non-negotiable.
And establishing those guardrails, making sure you don't build a beautiful app that drives your factory into a lake, is exactly why organizations look to the structural advisory frameworks provided by Twin Labs and AI Coach. You absolutely do not want to try and build this governance from scratch after someone has already made $1 million mistake. You have to build responsible AI capability and boundary testing from day one.
Exactly. You have to treat user engagement, psychological safety, and mathematical boundaries as core design inputs. They are not afterthoughts you tack on a week before launch.
All right, let's bring this massive topic to a close. We have covered the necessary transition from the mathematically perfect but operationally useless prestige models of the 2019 era to the fast, lightweight, containerized xDTs of 2026. We've explored the deep mechanics of surrogate modeling and how low-code platforms and APIs turn complex physics into mobile apps that shift workers can use in 4 minutes. We've detailed the critical 4-step playbook for deployment, the vital changing role of the technical expert from short-order cook to systems architect, and the terrifying reality of confident wrong answers if your governance is sloppy.
If we pull all of these complex threads together into a single narrative, the core thesis of the Twin Labs briefing is this. The technical barriers to digital twins are fundamentally gone. Containerization is solved. Surrogate models and PINNs are mathematically sound. Edge computing hardware is deployed. The engineering is solved. The only remaining barriers in 2026 are organizational will and human-centered design thinking.
So let me leave you, the listener, with a final provocative thought, something to really chew on when you walk into your next budget or strategy meeting. If I walked onto your operations floor right now, today, and tap to shift supervisor on the shoulder. How many people in your physical supply chain are actually using your intelligent models to make a decision today? How many maintenance engineers or sustainability leads are interacting with your multi-million-dollar AI? If the honest answer is zero, your first step isn't to go out and hire better mathematicians. It isn't to buy more cloud compute. Your first step is better operationalization.
That is the ultimate lesson of 2026. Treating daily operational utilization as the primary goal, rather than just chasing abstract mathematical perfection, is the single factor that separates the companies that are talking about AI in press releases from the companies that are actively profiting from it on the factory floor.
It all circles back perfectly to where we started. You can have the most advanced, beautifully engineered, aerodynamically perfect fleet of F1 cars the world has ever seen. But if you haven't bothered to build a dashboard the drivers understand, and you haven't handed the keys to the people actually moving the freight, all you own is a very expensive, very quiet parking lot. Thank you for joining us today. Visit the Twin Labs website for more business insights.